we'll be discussing Python bytecode. What is it? How can we use it? And why do I even care? What's very interesting about Python bytecode is that when we look at these states of Python code, when we start with our source text that we've written, we know that Python's parser converts this into an abstract syntax tree representation. We then take it to the next step. We then have this compilation step. And so with this compilation step, we're turning this tree into another form, into what's called bytecode. And I'm sure you've all seen this at some point. You can use the dis module in order to disassemble valid Python code, and we can see here that when I disassemble just x equals 1, very simple, very straightforward, I'm loading a constant, I'm storing it in a value called x, and then I'm loading none because it assumes that I'm working within a function, which I'm really not in this case. But you can see here that I can use a disassembly module in order to do these things. But what does this all mean? What's load const, store name, load const, etc.? Well, you can see here when I run just this very basic function, all it does is return 42. We get that same idea. We're loading a constant, returning a value. And if I inspect the code itself, you see that I end up with this byte string, right? This d\x01 s\x00, and we start to see a pattern. We see this pattern of one ASCII character followed by 2 bytes. One ASCII character followed by 2 bytes, and that's because Python bytecode as of Python 3.6 is guaranteed to be 2 bytes long. It's the ASCII character and then a byte. And so, if we break this down even further, we see something very, very interesting. And I want to compare this code info, and let's spruce up our code. Let's add one more assignment in here. We load this constant with an argument of 1, and then the representation, right, the value we're working with is 10. Well, what this 1 points to is actually all of the constants loaded into the namespace of this function. And so this constant 1 refers to 10. And so whenever you see this third column over here, we're actually inferring from this constants, from the variable names, which one are we grabbing, and then what's the value of the thing that we're grabbing. So store fast, I know that has to do with variable names. It gets the 0th thing. The 0th thing under variable names is x, and that's why we have x over here. Over here, you see these numbers increasing by 2s, and that's because every bytecode instruction takes 2 bytes, as I mentioned, I believe Python 3.6 or later. And so, and all the way over here on the left is the original line from the original source code. So this would be line 10 in my source code, line 13, so on and so forth. And the very, very neat thing about Python bytecode is that in Python, I can run, if I define this function that returns just x plus y, I can run valid Python code. I can feed it 2 integers. I can feed it 2 strings. I can't feed it a mix, right? But if I disassemble this function, it's the same thing. It's not rewriting the bytecode when it encounters, right, something at runtime. This binary add has to be dynamic enough in order to work with x and y if they're both strings, x and y if they're both lists, x and y if they're both integers or floats. It has to be dynamic in the bytecode itself, right, in that logic. And so Python is all about this dynamicism. We don't really statically type things in Python, so the interpreter doesn't know in advance if x is going to be a float or if x is going to be a string. And that leaves things open to interpretation. Python has to be kind of vague enough in order to work. Very interestingly, if I have a decorator and all it does is just pass the function through, well, before the Python's decorator syntax was added in, I had to define a decorator like this. In order to apply it, I had to reassign it to the variable with the same name. And you'll see in my abstract syntax tree, I define some functions, I define some more functions, and then I assign, right, f1, the value of calling my decorator function on the previous function called f1. And if I do the same operation with a decorator, the abstract syntax tree looks quite different, right? I'm now, instead of calling a function, I'm passing a decorator list into function def. That's quite different representation at the level of the abstract syntax tree. However, when I disassemble both of these codes, we can see, I'll just show you the top code first. we can see that loading a constant, making a function, storing a name. Loading a name, calling a function, and storing a name. And when I go ahead and uncomment this with the actual decorator values, we see almost the exact same bytecode. And so we can reason about this decorator syntax in a very interesting way. This decorator syntax is not here to make Python more optimized, faster, anything of that nature. This decorator syntax, this at syntax, is for us, the people reading the code. It's for the human readable parts. And so what we want to do, or what we think about Python, is that the whole goal of Python was to be human readable in the first place and to have a very tight iteration loop in our development. And it does very well at achieving both those things because since this language is first compiled and then interpreted, we can do a lot of steps, a lot of coercion. We can take these two parallel lines of thought, this apply a decorator by manually overwriting it, or apply a decorator with this at syntax, and we can coerce them to be the same exact bytecode so that the version of Python, right, the interpreter that's running this bytecode, doesn't have to care. And that's one of the big reasons that Python breaks these things into two parts, is that we can have these very parallel ways of doing things, and we can distinguish, we don't have to distinguish them down the line, we can distinguish them at a very high level. And so if you look, this is the abstract syntax tree of an if-else statement versus an if-else expression. And so just for your familiarity, this if-else statement is up here for flow control, and down here I have an if-else expression. And at the level of the abstract syntax tree, we see an if up here, and it has a body, right? When it's true, it does this. When it's false, it does that. And we're doing the same thing. We're assigning x and ellipses. But in the if expression, now we see the abstract syntax tree has its own representation of an if expression, what the grammar looks like for that. But again, at the level of the Python bytecode, it doesn't care. The only thing that it cares about is lines 2 through 5, right, is an if statement, load name, call function, pop jump if false. And then we look at the generated bytecode for the if expression, load name, call function, pop jump is false, and it's the exact same ordering of things, except this doesn't have as many breaks in its control flow, whereas this has 3 breaks in its control flow. And this does not mean that it's more, the if expression is more optimized and you should use it because you're going to save half of a nanosecond. No, the whole point is that Python does not care if you write your if statement using an if ... else or if you use an if expression. The generated bytecode is near identical. Another very interesting approach, what can we do with this bytecode now that we've kind of explored it and understood how to parse it and reason about it? Well, we can look into some very interesting issues that Python has, or that you might encounter when you're writing Python. If I define a variable x equals 1, then call this function, and we can reason about, if I just print the value of x plus 2, this x will probably be grabbed from the global scope and I won't have to care. But if I later assign x a value to x and I run this, now I get this unbound local error. And what does that even mean? Well, let's take a look and reason about what Python is doing. Let's take a look at that code info and at the generated bytecode. We can see here that in line 7, we are executing, or we have our function, and what we're doing, we're loading a constant of 2, and we're going to store that into x, and x is the 0th variable here, okay? And then we're going to load a constant none, and we end up returning that. The interesting part about this is that Python uses this store fast. And if I were to get rid of x equals 2, well, now Python first loads x as a global. This was completely omitted from the bytecode instructions if I uncomment x equals 2, right? We don't have load global x, we have load fast x. And whenever we hit this line of code, this load fast x, it's saying, wait a minute, we haven't loaded x. X doesn't exist here yet. X exists down here. So how can I load x if I haven't yet defined x? And this is what the global or the non-local keywords are all about. It's all about not just telling the bytecode, informing the bytecode where to get X from, but this actually happens at the level of the abstract syntax tree. You'll actually see, let me uncomment just a couple things. You'll actually see that we've introduced into the body this idea of a global node. And all this does is just tell the bytecode where to look for this value X. So we're not doing anything too wild, too crazy. We're just changing this load global X, or this load fast, or this non-existent, right? Just load fast X into load global. And that's all the global keyword does for us. And now that we've changed it to global, we'll see that this code actually does run and it does work. And we get the output that we expect, and we change the value of X to 2 in the end. And so we can use the bytecode and we can use the abstract syntax tree in order to reason about some of these Python oddities. Some of these, if I had to go dig through 600,000 lines of CPython in order to figure out this unbound local error, I'd probably be spending the better part of an entire workday just trying to figure it out. But just by looking at the bytecode that's generated, I can reason about, oh, that's what Python is doing. And if you've ever tried to use a try and except and capture that error for later reporting, maybe I don't want to do anything with it right away, but later I want to do something with that error, we see that, oh man, name error E is not defined. And if I do E equals E, oh, I still get this weird name error, but I'm assigning it to a variable. Like, this is definitely a variable. But if I do F equals E, and I print F, all of a sudden it works. I just renamed the variable. What's going on? Well, let's take a look at the generated bytecode. And we can see right here that when Python captures this exception and stores it into a variable, as soon as we leave the scope of that try except block, it deletes the reference to that variable. So if we that's why we can circumvent it by making a new variable, because it just deletes the name E. It does not deleting the name F. And so we can see that it's creating F, right? But it's only deleting E at the end of our try except. And so Python does about this. If you were to dig through a little bit of code, you can actually find some comments about why it does this, and that's essentially we need to decrease the reference count to E, or else Python might accidentally hold on to this exception much longer than needed, and it will have to be cleaned up by the garbage collector. But we can always assign it to a new variable that's not tracked by the exception syntax or the exception logic, and we can do things with F. And so this is one of the uses of disassembling your Python code into bytecode, is you can take simple functions, simple statements, and reason about them in ways that you could not before. This final step, or this next step of translating an abstract syntax tree into bytecode, also gives us a couple of times or a couple of points that we can introduce optimizations. Now, Python doesn't heavily optimize at the level of our abstract syntax tree because we want this compilation step to be extremely fast. And if we wanted something to be heavily optimized, well, Python's probably not the language that you should be choosing if you care that much about speed. And so what I want to point out here is that in our top function, it has a body of a binary operator. This is just addition, right? And it's going to add X and it's going to add Y. And as I said before, Python's dynamicism lets us do this without really caring too much. In our bottom function, we're going to add 1, 2, 3 plus 4, 5, 6, and we see that right here. Binary operation, left is 1, 2, 3, right is 4, 5, 6, and we're doing an addition on them. And so the level of the abstract syntax tree, it doesn't care. But at the level of the bytecode, right, the next step into making our code dynamic and into runnable, we see that we are performing a binary add on X and on Y. But in our bottom function, all of a sudden that binary add is completely gone. In fact, it's retrieving 579, which happens to be the output of 1, 2, 3 plus 4, 5, 6. This is an optimization called constant folding. We've essentially identified an expression, right, 1, 2, 3 plus 4, 5, 6, that is comprised entirely of constants. And we said, well, the Python interpreter doesn't need to deal with this after the bytecode. Let's just optimize this just a little bit. It's such an easy optimization to do. Let's just do this addition right now at the compilation step, because there's really no wrong way to reason about this. And this lets you keep numbers apart, right? If I were to have parts of a day or minutes, hours, and seconds represented as integers, and I were to do multiplication in order to coerce them all into seconds, right? So your minutes are like 5 minutes times 60, and your hours are 5 hours times 60 times 60, right, to get to the number of seconds. The Python bytecode will optimize that for you, so you don't need to really worry about the performance impact of not reducing your constants in your mathematical expressions. And so that's just one of the few optimizations that Python will do when coercing your abstract syntax tree into a representation.